So just a notification about where we were with this chapter on Laplace transforms. We've seen the definition of the transform. We've looked at some of its basic properties. And not last week, because Stephen took all the lectures last week, but the week before we met the technique for how to solve differential equations, making use of the Laplace transform. That was kind of the culmination of the chapter, so to speak. We had this roughly 4-step process. So faced with the differential equation like this one in equation 2.24, this is back on page 40 something of the notes, 48. These 4 basic steps. The first step is to transform both sides of the equation. And in doing that, you're using linearity to break up the transform of the left-hand side into the individual transforms of the various bits that are added together. Because it's a differential equation, those various bits are all various scalar multiples of a derivative of the unknown function y. The transform of derivatives properties allow you to express all of those transforms of those derivatives, express them all in terms of the transform of the unknown function y, multiplied by various powers of the new variable s. But essentially, you get the left-hand side as depending just on the transform of the unknown function y and the various polynomial factors in x. And hopefully we can transform the function g of t in the right-hand side. You also get various constants coming up in those transforms of derivatives. Those constants are the various initial values of y and its derivatives. And in a typical ODE problem, those are often provided to you. Because at least in some kind of, in most kind of engineering or physics settings, those initial conditions are known to you. So it's part of the setup of the problem, and we're interested in tracking the evolution of something over time. So very often we know about the initial conditions, or equivalently some kind of boundary conditions on the problem. So you specify any constants that you can using information. And then 3 is you kind of algebraically solve the transformed equation, and you'll get an expression for y bar, the transform of the unknown function. You'll get an expression for that as a function of s. Some kind of rational function of s, quotients of polynomials in s, which you then have to take the inverse transform of. And this last step, while it's a bit glib as it said there, you just take the inverse transform of it. But if you're doing it pen and paper, armed with the table of Laplace transforms, quite often there'll be some preparatory manipulations you need to do, such as using partial fractions or re-expressing the denominators, factorizing them, and so on, in order to cajole the thing you're looking at into a linear combination of things that are on the table. So you can read off the individual inverse transforms and recover the original function y of t, which will be the solution to the original ODE. So we looked at some examples of that. We'll look at a few more examples in due course. But what we want to do now is to look at a way of kind of widening out the domain of the problem. Or what that means is kind of increasing the scope of our technique. Increasing the scope of our technique for solving differential equations. Okay? So what that means is bringing in more functions. Bringing into the discussion some other types of functions. Okay, so the first function we're going to look at is called a Heaviside step function. It's named after this English engineer, mathematical engineer called Heaviside. Now, in some ways, this is an extremely, almost insultingly simple object. Okay, it's a function. How complicated a function is it? Maybe you're expecting a very complicated function. And it's difficult to draw the graph of it. Well, it's easy to draw the graph of half of it. Doesn't look like a very complicated graph. Basically, the Heaviside step function is 0 for every negative value of t, and it takes the constant value 1 for every positive value of t. Big deal. Okay? Extremely simple. I mean, the only simpler function would just be a constant function that's always set at the value 1. It's a little bit more tricky. Half the time, it takes the value 0. Half the time, it takes the value 1. But the idea of this function is this is used to model a process that, let's say, switches on at time t equals 0. So up to time t equals 0 is a function which takes the value 0. So it's some kind of signal or factor in a problem which is turned off. And then at this magical time t equals 0, it switches on, and thereafter it takes the value 1. 0 means switched off, 1 means switched on. I won't quibble too much about whether you regard it as taking 0 for every t less than or equal to 0. The t equals, sorry, or not. That should be a 0. T greater than 0, not 1. Whether you regard the value it takes at t equals 0 exactly as being 0 and 1 is neither here nor there. Okay? It doesn't matter. But the point is it's switched off for negative times, and at t equals 0, something magical happens and this thing switches on. And we can use it to build more complicated switches, let's say. Something being switched off with a value 0 and then being switched on with a value 1. That's about the most simple kind of switch you can have. Now, we don't need a whole family of different step functions. We can just, by manipulating this step function, we can produce different kinds of switches. So for instance, we can move the location or timing, if you like, of the switch. Well, how do you do that? How do you produce a function which, instead of doing the switch at t equals 0, does it at some other time? Well, basically what you want to do is you want to take that graph and you either want to translate the graph to the right or translate the graph to the left. The time of switching to some other value. Respond to what is graph of something right or left on the axes, that corresponds to shifting the argument t to the function. The Heaviside function t, and this is the conventional way we write it, you could do t plus a, but t minus a. But you see, it's still the same Heaviside step function, so it's still just going to take two values, 0 and 1. But the Heaviside step function was defined that it takes the value 0 when its argument t is. So this will still do the same thing. This function will take the value 0 when its argument is negative. But t minus a being negative, that's the same as being t less than a. And taking the value 1 when the argument is positive, or non-negative when the argument is past 0. So when t minus a is past 0, that happens when t is bigger than or equal to a. So by simply shifting the argument to the function by a constant, let's say a is over here, then suddenly we have this function. Just put arrows there just to indicate it continues that behavior left and right. And now we've got a switch which at least is switching on at a different location. Okay, still not looking that complicated, so we can switch something off and on at various times. But this is quite a flexible idea, so there's some further examples here. Example 2.11. And of course, being able to model things getting switched on and switched off is an important idea to be able to model things in engineering and physics. So in this example here, let A be less than B. What about this thing? Which is h of t minus a minus h of t minus b. So this is a difference of two shifted Heavisides. The first one on the left has been shifted by A. The second one we're subtracting has been shifted by B. If you think about the behavior here, how does g of t behave? Well, okay, it's a linear combination of Heavisides. Heavisides behave according to whether their arguments are positive or negative. And the locations at which these various parts change from being, where these arguments change from being positive or negative, that happens at A and happens at B. But everywhere else, nothing is changing. So if you consider some very small argument, t less than a, so a very negative time, t less than a, then both of these are switched off. So you just do 0 minus 0, so this thing is equal to 0. And it will always be equal to 0 for every value of t less than a. But then when t passes through a, this first Heaviside here switches on. Because when t passes a, h of t minus a jumps up to the value 1. And that happens before you get to b, because a will assume a is the smaller one. So when you get past a, the first Heaviside switches on, and the second one is still switched off because you haven't got to b yet. Minus 0, in other words, it's 1. And that remains the case until you get to b. So until you get to b, it'll always be that this h is switched on and that one is still switched off. So you still always have the value 1. Up until you get to b. But then once you go past b, both arguments now, t minus a and t minus b, both arguments are positive. Both Heavisides are switched on. Minus 1. So you're back to 0 again. And you stay at that value forevermore, because nothing else is going to happen. For every larger value of t, these two Heavisides are still taking the value 1 each. So when you subtract them, you'll always have 0. So this is, the next most interesting kind of switch, something that's switched off, switches on for a bit, and then switches off. So if we were to draw a graph of it, let's just assume A and B are positive. So you've got some signal that is switched off. It's taking the value 0. But then between A and B, it takes the value 1. And once you get to B, it switches off again. Okay, that's a little bit more realistic. Most things we switch on, we tend to switch them off again. Lights, machines, forces, effects. So something happens for a certain period of time, and then it stops happening. So this is like switching on and off. But it's interesting how we can do it using the same basic function, using the Heaviside step function. Example 2. Is that okay? Any questions about that example? Or? So analyzing it, we wanted to decide what its value was for every value of t. Well, it's made of Heavisides, which change at A and change at B. So the only significant things happen as you pass through the values A and B. Otherwise, it's a constant function. And because of the way it's constructed, because of the difference, it means it's going to be 0, 1, or 0. The next example looks at this function, f of t, which is defined as 1 plus cosine of t times, again, this construction, h of t minus a minus h of t minus b. Well, understand this factor here. That's the factor g up here, 0, 1, 0. So f of t will behave very similar. It'll be equal to 0 for t before a, 0 for t beyond b. But between a and b, g takes the value 1. So we got 1 for this big bracket here. And of course, when this big bracket is 0, it makes the whole thing f of t equals 0. It doesn't matter what you've got here if you're multiplying it by 0. Well, when this second large bracket is equal to 1, then we've just got whatever the value of this bit is, 1 plus the cosine of t. So this, in a way, is an example of the next most kind of interesting switch. Okay, something that switches on and switches off, but the signal that it switches on is just a very boring, constant, monotonous signal of strength 1. At least this is a little bit more interesting. The signal that it switches on is 1 plus cosine of t, which at least varies a little bit, quite periodically and understandably. Now, we don't know exactly what A and B are, so I won't know exactly what the value of 1 plus cosine t is going to be at the endpoints. Vaguely, well, remember, cosine of t oscillates between plus and minus 1. So if I'm adding a 1 to it, 1 plus cosine of t is going to oscillate between 2 and 0. Yeah? You got 1 up here, 2 there, 0 there. So it's some kind of a little bit more interesting. We've got something that's switched off, but in this interesting period between A and B, it switches on some kind of non-trivial signal, some oscillating signal. Again, this could be the current flowing through an electrical circuit. This could be some kind of driving force, driving a piece of machinery. Any kind of a thing. But it's interesting, again, how flexible the Heaviside step function is. We don't need a whole family of different switching functions. Just this basic idea of something going from off to on. If you manipulate it and do combinations of it, you can build switched signals, if you like. The third example goes in the other direction, kind of, in that it gives you, you start off with a piecewise defined function. These expressions where you've got a function defined in, well, you can call them case-wise defined function or a piecewise defined function. It's not defined by a single formula, but by different formulas for different pieces of the function, different cases of the argument. So this one is expressed as 0 for t less than 0, t for 0 for t between 0 and 2, and 2 if t is bigger than or equal to 0. Draw a graph of V and find a definition for V not utilizing different places, involving just the Heaviside step function. So there's 0, here's 1, there's 2. So interesting things happen to this function at the value 0 and 2. So for t less than 0, it's just 0, so you just have this 0 level graph. Values of t between 0 and 2, the function is following the formula t. So it's just the 45-degree line, y equals t, v equals t. And thereafter, once you get to t equals 2, it changes again to just be the constant value 2. Okay, so it's a kind of a graph of the interesting portion of this function. Well, you can think of this let's think of this as being, think of this graph as being made up of these 3 pieces. So I want to find the expression for this involving Heaviside functions. So v of t we can think of as the sum of these 3 functions, v1 plus v2 plus v3, where the function v1 of t is equal to 0 for all t. v2t is equal to t for t between 0 and 2 and 0 otherwise. And v3 for t greater than or equal to 2 and 0 otherwise. So we just kind of isolate the 3 different types of behavior. B, and each of these now can be expressed in terms of Heaviside step functions. This one is, well, okay, this one is easy enough. It's just equal to 0 all the time. We don't need anything more to describe it. This one, so it wants to be the value t just between 0 and 2. So this will be h of t minus h of t minus 2. We already described how differences of Heavisides are switch something on for a certain time period. So to switch something on between 0 and 2, you do h of t minus h of t minus 2. And this function v3, which is to be the value 2 for every t beyond 2, that's going to be 2 times h of t minus 2. So our v of t sum of these three things, so it's 0, so I don't need to include that. It's going to be t times h of t minus h of t minus 2 plus a 2. 2 times h of t minus 2. And the fact you've got the same Heaviside function here in two places, so you might want to rearrange that as being t times h of t, and then another factor with h of t minus 2, and you could express that as minus h of t minus 2 times h of t minus 2. That example shows you, see in the previous two examples, we started off with the Heaviside expression and then investigated and found the piecewise definition and what the graph looked like. Here we're starting with the piecewise definition. Some kind of signal, this is like some kind of ramp signal, something which goes from a 0 level to a 2 level, not immediately with some instantaneous shock, suddenly being equal to 2, but rather some evenly increasing function over some ramp up period between 0 and 2 to get from the value 0 up to 2. So it's a bit of a gentler switch on rather than just instantaneously switching on something. So at least from that description, by breaking it down into pieces, we can arrive at a nice description in terms of Heavisides. Of course, the function v of t is still essentially a piecewise kind of thing. It's got different behaviors and different intervals, and they switch on and off. But at least it's some kind of a technical device to. It doesn't look on the page like a piecewise defined thing. It's just v of t is defined as a combination of this function h. So the piecewise or switching aspect is kind of incorporated into the h's. You're not seeing it explicitly in the formula. So the function h incorporates or embodies the switching behavior. And it gives us this single device, this single function that can do that switching job in various ways. And what our aim is we would like to kind of admit this into the fold and be able to solve differential equations featuring the Heaviside function. So we aim to be able to solve ODEs featuring H. And what that basically amounts to is being able to take the Laplace transform of H. So that's something we'll need to investigate. Being able to take the Laplace transform of H and also products of H with other functions. We'll also need to be able to do that, where you have some function multiplied by H. The other type of function, which you see there, is the Dirac delta function. I'll put function in quotes. Strictly speaking, it's not a regular real valued function. This is named after the British physicist Paul Dirac, around most of the 20th century. It's called the Dirac delta function. This function kind of has a interesting graph, if you like. Basically, it's 0 everywhere, so it's kind of hard to draw the graph of it, really. Dirac delta function is 0 everywhere except at the value 0. And this is why we don't really, strictly speaking, want to call it a function, but at the value 0, it takes the value infinity. That's kind of suggested by sticking that arrow there. It's really high up at infinity. So this is used, so this is like some kind of signal which is basically off everywhere but has a single spike. Or a single kind of impulse or shock that's delivered to a system at time 0. So nothing's happening, and at time 0 there's a big bang, so to speak, and then nothing else. It's more properly called, it'd be more rigorously defined as something like a distribution. It is maybe something which doesn't have an existence as a strict function, but it does have an existence as something you can integrate. So you can also set up the Dirac delta function as something that is 0 almost everywhere away from 0, but when you integrate it, you get an integral of 1. That seems silly because it doesn't look like there's any area under the graph, but of course in this very tiny thin sliver here, there's an infinite height. So maybe you can fit in area 1 there. Okay. Just like for the Heaviside function, we can relocate the spike as before. Like we relocated the switch with the Heaviside function, we can look at delta of t minus a. So this will be in this infinity value at t equals a, and 0 otherwise. Otherwise, for t, there's a, and there's the spike. Again, we would like to be able to solve differential equations that feature this Dirac delta function. So maybe as a, we'll continue this in the later lectures today. But as a first stab at some of this, we go to page 55. I will do some of the examples. We'll do some more examples with you today as well. So if we start thinking about Laplace transforms of these, then they're listed on the, if you look at the table of Laplace transforms, there are entries on the second page of it for the Laplace transforms of these new functions, Heaviside step function and the Dirac delta function. But theorem 2.4 is the transform of the Heaviside. We can deal with it in general, deal with the location of the switch at any position. And this has a nice enough transform. It's this exponential term, e to the minus as over s. That's listed on the table. And say, just this transform on its own won't be enough, because we've already seen examples where we're showing the Heaviside step function multiplied by other functions. Remember, the Laplace transform is not multiplicative. We never say the Laplace transform of the product of two functions is the Laplace transform of f times the Laplace transform of g. So just because we know the Laplace transform of this won't mean we automatically know the Laplace transform of some function multiplied by this in the examples of switches. So we'll need a separate property for how to deal with those. But at least let's just focus on a kind of simple switch going from 0 to 1. And these are interesting as well because they're nice little calculations involving the definition of the Laplace transform. So I'm trying to say, well, when you look at the past exam papers, you see that sometimes I've asked these in the past. They are nice little exam-sized questions in a way. So they're definitely good things to know, and they're nice exercises involving the definition. So, without thinking, we can write down this because that's the definition of the transform. How do you take the transform of something? You integrate e to the minus st multiplied by whatever the something is, dt. Okay, we're assuming a is bigger than 0. I mean, the normal way these problems are described is the experiment begins at time 0, and you want to look at the evolution of it after that. So the setup at time 0, and something interesting is going to happen at a. Something's going to get switched on. So a is some positive time. Now, as we said before, okay, this looks kind of awkward now. We got an integral involving this new function h. Really, it's very simple. It's not that complicated. It's either 0 or 1. If it was 0, we could deal with that easily. 0 times the exponential is just 0. You're integrating 0. Not much is going to happen. If it's equal to 1, then you're just integrating the exponential, which we also know how to do. So you know how to handle it if it's 0 or 1. It does that kind of behavior. Well, everywhere between 0 and a, the Heaviside is 0. Everywhere beyond a, it's 1. And integration has this very nice property that you can split the interval of integration up, and you break the single large integral into subintegrals. Results together. That's the way integration works. Think about integration as area under the curve. You can just kind of cut the page somewhere, say, well, I'll talk about this area up to this point, and then from that point on, I'll calculate separately as another area. Just one integral, cut the region of integration up into bits. So as we said, this is very easy to handle. 0 times this is just 0. Integral of 0 dt, 0 to a. Not that surprising that you get 0. Okay, it's easy enough to deal with. This, a 1 is easy enough to deal with. Get e to the minus st dt. An exponential integrates to itself, essentially, except we need a bit of a chain rule here, because it's e to the minus s times t, so we need a minus s to divide by. We just integrated this with respect to t between these limits a and infinity. So you need to do the evaluation here. This means take the limit of this expression as t goes to infinity. Remember, these are limits for t. You just integrated with respect to t. So as t goes to infinity, well, provided the real part of, I'll still say the 0 plus part of s is positive, that e to the minus st will go to 0. And then it will be minus, and the evaluation of t equals a is just by substitution. That's provided the real part of s is positive. We discussed that when we looked at the definition of the Laplace transform originally. So yeah, basically it's just what we expect. E to the minus sa over s as required. Okay. So just a nice, straightforward application of the definition of the Laplace transform. gets us that without too much bother. Okay. Any questions about that, or slight queries that you have? Okay, I might just end ever so slightly early, just because I'm going to be seeing you for another 2 hours of lectures today, and then some of you in the tutorial. So we'll make more progress with this, and I'll see you at 1, then in Jeffrey Mountain. Just go easy on you for the moment. If you've got any questions, feel free to come up.